Hello, I'm Trevor and I run the Chemistry 2 workshops for CASA here on campus. Today I'll be going over an example problem that deals with the concepts of gas laws and stoichiometry. We'll be talking about chemical hand warmers. You may have seen these devices that are used in gloves or pockets to keep your hand warm during cold days. We'll be talking about specifically this type of chemical hand warmer. It's a porous packet filled with a powder. And that powder turns out to be iron, and there's a catalyzed iron oxidation reaction that occurs which produces heat. For simplicity's sake, we'll say that this reaction goes as follows. Iron plus 3/4 oxygen goes to iron oxide and just iron oxide. So here we're assuming this is going to iron 3 oxide. We'll just make the problem simpler. So the part A asks if you have a heat pack that has 200 grams of iron in it, so we'll just assume it's a really big one, and it's left in a room at 20 degrees C at 1 atmosphere with a volume of 50,000 liters. What reagent is limiting? Will it use up all the oxygen in the air first, or will all of that iron get oxidized first? So let's figure out how many moles of each reactant we have. That's how we're going to figure out which one's limiting. The one that there isn't enough of will be the limiting reactant. So if we have 200 grams of iron, we divide by iron's molar mass, which is 55.845 grams per mole, then we get 3.58 moles of iron. So that's a fair amount of iron, 200 grams. Now let's see how much oxygen we have available. Here we can use universal gas law. The R value that I'm going to use is 8.3144 Pascal meter cubes per mole Kelvin. So in order to make all the units for that work, I'm going to have to turn atmospheres into pascals. So we use the conversion. 1 atmosphere equals 101,325 pascals. So coming down here for gas laws, we have 101,325 pascals. That's our pressure times our volume. We said 50,000 liters, so that's 50 meters cubed, because there are 1,000 liters in a cubic meter. You should be able to figure that out knowing that a liter is a decimeter across, or a liter contains 1,000 cubic centimeters. We'll divide by R, the gas constant, 8.3144, and this is in Pascal meter cubes per mole K. Cancel out all these units. So pascals cancel out, meter cube cancel out. We want moles, so Kelvin's the last thing that we need to multiply by. Down here, it's 20 degrees C. So this is the conversion to Kelvin. So this is 293 Kelvin is 20 degrees C. And then we're going to multiply by one more factor, and that's 0.2. Why are we multiplying by 0.2? This is the number of moles of oxygen per mole of air. So the air is about 20% oxygen. So if this is going to give us the moles, right? If we have PV equals nRT, we're solving for N. So this is going to give us the moles of air. But we don't want air. Oxygen is what's reacting up here, so we want 0.2 moles, or we want the moles of oxygen. So there are 0.2 moles of oxygen per mole of air. So we get 20% oxygen in the air, and that gives us the final value of 415.9 moles of O2. So, which reactant is limiting? Well, we have 3.5, a little over 3.5 moles of iron and 416 moles of air, or of oxygen, specifically of oxygen. That means that iron is going to be the limiting reagent because we're going to run out of iron first. Remember that you do have to check this ratio. So you don't need a whole mole of oxygen per each mole of iron. You only need 3/4 of a mole. So you really only need 3/4 of 3.5 moles of oxygen in order to get this reaction. So we have plenty here. So iron is going to be the limiting reagent. Oxygen will be in excess.